Swayam Prabha. Digital India. Educated India.
Hello everyone. In today's class, if you recall, in the last class we stopped at the concept of the injection velocity in a MOSFET. In today's class we will discuss that concept in greater detail. So that's I would say the most important idea in the MOSFET transport, that is to understand the injection velocity right at the top of the barrier in the MOSFET. And in this case we are considering a ballistic MOSFET and we are trying to understand the injection velocity in a ballistic MOSFET. Before going into those details, let us quickly review what we have seen so far. So what we have seen is that in steady state in a ballistic MOSFET, the charge in the channel, which is the inversion charge, is given by this expression, and this comes from the Landauer transport model. This is actually another form of this expression, which is Q times d F1 plus F2 by 2 d E, where this negative sign is there because the charge involved is the electrons, and d is the density of states, which is represented by d2d here. F1 is F1e, F2 is F2e. So this is the inversion charge can be calculated from this simple expression, and the current can be calculated, if you recall, from this expression for a ballistic MOSFET. Okay. And as you can see, as we by now we have seen this in more details, in quite a lot of details, that depending on the factor in this integral, we will obtain Fermi-Dirac integrals of various orders when we simplify this integral. Okay. So a Fermi-Dirac integral of order plus half is obtained when we have square root of E times Fermi function in the integral. Okay. So this is the current expression that we obtain, and the charge expression is this, and if we try to understand this expression in our more general form of current expression, which is given by this expression, I is equal to W times Qn times average velocity. So in this case, this is what we obtain, and from here what you can see is that the average velocity right at the beginning of the channel is this ballistic injection velocity times this factor, which is a complicated looking factor involving various Fermi-Dirac integrals in it. So this is the charge. The ballistic injection velocity is just the thermal unidirectional thermal velocity times Fermi-Dirac integral of order plus half divided by Fermi-Dirac integral of order 0. And when a VDS voltage is applied across the system, then in that case this EFD is EFS minus Q VDS, and as a consequence of this, eta FD is eta Fs minus Q times VDS divided by KT. So now this average velocity is this total this expression, and this is what we will try to understand today. This is the central topic of today's discussion. So in a ballistic MOSFET, this is how the energy landscape looks like. This is the top of the barrier point, and the injection velocity is essentially the average velocity right at the top of the barrier, which can also be written as average velocity in positive x direction at x equal to 0 point when we have applied a VGS and a VDS voltage to the system. So, this is a more correct way or more elaborate way to write down the injection velocity in MOSFETs. So, as we have seen that this is how it looks like. Just before going into the details of its discussion, here this ballistic injection velocity, which is the velocity defined in equilibrium, which means that no drain voltage has been applied. What is the typical order of that velocity? Let us try to see that. Okay. So, if we do this calculation and if we just try to put various constants in this expression, square root of 2 kT divided by pi m star, you would realize that the order of this velocity is around 1.2 times 10 to the power 7 centimeter per second. So, this is quite high a velocity, and generally the velocity saturates in MOSFETs, and one of the reasons of velocity saturation is the scattering in the MOSFET. As so, typically in long channel MOSFETs, the velocity is dependent on the electric field in a linear way. So, as the electric field increases, the velocity increases, but after a certain electric field, because of the increased collisions as well, the velocity saturates. But the velocity also saturates in this case as well. Okay. And even in the ballistic MOSFET, and in the ballistic MOSFET there is no collision in the channel. So, that is the central topic of today's discussion: how does the velocity saturates in a ballistic MOSFET, and what is the underlying physical principle of that. So, here we show the injection velocity as a function of inversion layer density, as a function of the charge density, and as you can see that it is actually, as the charge increases, inversion layer density increases, the injection velocity also increases because of these Fermi-Dirac integrals involved in the expressions, and this is a simulation of these expressions. Okay. Yeah, so this is the main topic here, that and this is a real simulation for a ballistic MOSFET and taken from this reference, where it is taken in which it is taken from a paper. And so, this calculation has been done by assuming the Fermi-Dirac statistics in the ballistic MOSFET, and this has been done by assuming the Maxwell-Boltzmann statistics. As you can see that although their values are different, but they are fairly similar to each other, although not exactly the same, but they can explain the behavior of electrons pretty much in the same way. And as you can see that the current is saturating after a certain drain voltage, which is in this order, which is, it starts from for low gate voltages, it start from 0.25 to 0.3, but typically when the gate voltage is also high, it starts from 0.4 volts and above. So, from 0.4 volts and above, drain voltage, when VDS is 0.4 volts and above, or maybe 0.45 volts, in that case the current is getting saturated, and this is from a real simulation of a ballistic MOSFET. And this is what we will be trying to understand today: why is this saturation taking place even though there is no scattering in the channel. And this is the plot of the average velocity as a function of the drain voltage, and as you can see that initially the velocity is linearly dependent on on the drain voltage, but for higher drain voltage it starts saturating and it approaches the unidirectional thermal velocity. So this is precisely the reason that this current is getting saturated after a certain drain voltage. So now we need to understand what is the reason for the velocity saturation in ballistic MOSFETs. Just think about it, give it a thought for a moment, and then we'll go into the details of this idea. This is the energy picture of the device. When the VDS, the drain voltage is 0, this is how the barrier looks like, and when we have applied a certain VDS, this is how the barrier, or this is how the bottom of the conduction band looks like when we are applying a drain voltage to the system. So this expression, this particular expression, which gives us the velocity at x equal to 0 for a VGS and VDS, if we assume the Maxwell-Boltzmann statistics, and let me just quickly tell you why we can do that. So as you can see that the distribution of electrons is governed by the Fermi-Dirac distribution, and this is how it looks like. F is 1 by 1 plus E minus EF by KT, and in a typical semiconductor, when the semiconductor is non-degenerate, in that case the Fermi level is reasonably far away from the bottom of the conduction band. So for the electrons sitting in the conduction band, this quantity E minus EF is many KTs, is multiple KT value. So this parameter becomes larger as compared to 1. So ultimately this can be approximated by, this 1 can be removed from here by KT. So it becomes exponential minus E minus EF by KT, and this is the Maxwell-Boltzmann distribution. So for non-degenerate semiconductors, and especially in the MOSFETs when we are not applying high drain voltages, high current is not flowing, in that case assuming a Maxwell-Boltzmann distribution for electrons is not a very bad idea. It's a quite reasonable approximation, and if we do that, then the Fermi-Dirac integrals simplify pretty much, and Fermi-Dirac integral of order j actually can be approximated by eta exponential to the power eta f. So this order of the Fermi-Dirac integral is not relevant when Maxwell-Boltzmann statistics is there in the picture. So if we do that, then all these Fermi-Dirac integrals here, they can be approximated by the exponentials, and as you can see that on the numerator here, on the numerator we have Fermi-Dirac integral order half eta f d, so it can be approximated by 1 minus exponential eta f d divided by exponential eta f s, and the denominator is 1 plus, this is f0 eta f d exponential eta f d divided by exponential eta f s. So this is essentially this becomes 1 minus exponential eta f d minus eta f s divided by 1 plus exponential eta f d plus minus eta f s. So this actually simplifies too. So as you are aware that eta f s minus eta f d is minus q vds by kt. So this simplifies to exponential, this velocity, injection velocity at x equal to 0 is thermal velocity square root of 2 kt by m pi m star times 1 minus exponential q VDS by kT divided by 1 plus exponential q VDS by kT. So this is what becomes of the expression for the injection velocity while we assume the Maxwell-Boltzmann statistics, which is a fair assumption at low biases particularly and in equilibrium. So for small voltages, if this VDS is small, is very small, in that case this exponential thing here is q VDS by kT. If we expand this, this is 1 plus q VDS by kT plus 1 by factorial 2 q VDS by kT square and higher order terms. Even the second order terms can be ignored, so this can be approximated by 1 plus q VDS by kT. So 1 minus exponential q VDS by kT is essentially 1 minus 1 minus q VDS by kT. So it is just minus q times VDS by kT, and the denominator in this expression, which is 1 plus q VDS by kT, this is 1 plus 1 plus q VDS by kT. So it is 2 plus q VDS by kT, and this VDS is very small as compared to kT by q, so it is just 2. So this thing here, this velocity for small voltages, for small VDS, it is Vt times, in the numerator we have minus q by kT VDS, in the denominator we just have a factor of 2. So this velocity is actually Vt times 2 kT by q times minus VDS here. Okay. So if we multiply and divide by length here, this becomes the electric field in the device. So it is VTL divided by 2 kT by q times the electric field. And if we compare this to our conventional expression of the velocity, conventional relationship between velocity and electric field, which is that the velocity is mobility times the electric field. So this, the first term here, which is Vt times L divided by 2 kT by q, that will just be the ballistic mobility, or that can assume to be the ballistic mobility in the system. So if we compare this to this, in the ballistic case, this mu b will be equal to Vt times L divided by 2 kT by q. So this is an important expression for the, if we need to, if somebody asks you what is the ballistic mobility for a given ballistic MOSFET, this is how we calculate that. We first calculate the unidirectional thermal velocity, and then by, if we know the channel length, and then these are just the constants, using all this we can calculate the ballistic mobility of the channel. So this I would say that this was a small side discussion here, but what our central aim is, that is to understand the velocity saturation in the ballistic MOSFETs, why this is happening. So for that we need to understand the velocity from a microscopic point of view. We need to understand the distribution of velocity in the device. So the device is something like this. In an actual MOSFET, the source, the drain is there, even the gate is there, and there is a small channel region here which is just like a 2D device. This channel is almost like a 2D channel. So that's why most of our analysis, which is for a 2D channel, will hold true in this case. So our analysis is for a device something like this, in which there is a source, there is a drain, and the channel is a 2D channel. Even in an actual MOSFET, the channel is a quasi 2D entity there. So this is the length, this is the width, this is, let's say, x direction, this is, let's say, the y direction in this. So we need to, in order to understand the velocity saturation, we need to understand the distribution of velocities. Whenever an electron starts from the source side to go to the drain side, what is its Vx, what is its Vy, and how these velocities are distributed for various electrons in this device. So that's what we need to understand, and we will start with the Fermi-Dirac distribution function in order to understand that. So the Fermi-Dirac distribution function says that this is how the electrons are distributed in various energy levels in the device. And just now we saw that for a non-degenerate semiconductors, we can approximate this, this factor is large, so this 1 can be ignored. So ultimately this becomes exponential minus E minus EF by KT, or EF minus E by KT. Okay, so this is what becomes of the Fermi-Dirac distribution when we are considering the non-degenerate semiconductors, because this parameter is many KT value. So this 1 can be ignored, and it boils down to the Maxwell-Boltzmann distribution of the electrons. Now if we look at just at the top of the channel at x equal to 0 and try to understand the velocity here, we'll come to that. So what is this E here? This is the total energy of the electrons, and if we draw the bands, this is the valence band, this is the conduction band, and the total energy of any electron that is sitting in the conduction band is E is EC plus half m v square, where this m is m star, which is the effective mass, and v is a 2D velocity, so it can be broken down in its components. So v square is vx plus vx square plus vy square. Okay. So the total energy of the electron that is sitting in the conduction band is the potential energy, which is the bottom of the conduction band, plus the kinetic energy. And if we put this energy value in the Fermi-Dirac distribution function here, which becomes a Maxwell-Boltzmann distribution. So if we put E is equal to EC plus half m star v square in this function, what we obtain is the distribution of various velocities. So what we can say is that the distribution of velocities is exponential EF minus EC, or E is being replaced by EC plus half m star v square. So this will be EC minus m star v square by 2 kT. This kT is the common denominator here by kT. So this can be this constant part can be taken out, so which is exponential EF minus EC by kT times exponential minus m star v square divided by 2 kT. And now this v square is actually the two-dimensional velocity. So this v square is vx square plus vy square. For an arbitrary electron which is starting in the channel, so if there is this arbitrary electron, it will have this is the velocity at any angle, it will have a Vx component and it will have a Vy component. This is the net velocity, this is source, this is drain, and this is the channel. So this is how we obtain the distribution of velocities in the ballistic MOSFET. And what is the meaning of this distribution of velocities? So this is in a way the probability that an electron will have a velocity v in the channel. And if we simplify this further, it will be this v square can be written down as vx square plus vy square. So this velocity distribution function can be written as f naught vx vy is equal to ef minus ec by kt times minus m star vx square plus vy square by 2 kt. So this velocity distribution function, which is also known as the Maxwellian distribution of velocities, is the probability that a certain electron will have the Vx velocity in x direction and Vy velocity in y direction. That will be given by this function. That's why it is known as the velocity distribution function, also known as the Maxwellian distribution of velocities, because the Fermi-Dirac distribution has boiled down to the Maxwell-Boltzmann distribution in this case. So now we can see how this saturation thing is coming in picture in our case. So in a MOSFET, typically if we just draw the barrier in the MOSFET, this is how the barrier is without any VDS. This is the source side, this is the drain side, and this is how the barrier becomes when a drain voltage is applied in the system. So there would be some electrons that will go from source to drain, and there would be some electrons that would go from drain to source. So some electrons will be traveling in positive x direction and some electrons will be traveling in negative x direction, and the channel is along the x direction. So we will be focused more on the Vx component of the velocity, and for the electrons traveling from source to drain side, or positively traveling electrons, or electrons traveling in plus x direction, this EF will be EFS, because the source is the electron where they are coming from. And the electrons that are coming from the drain side, the drain contact will be the origin of the electrons. So instead of EF, we will have EFT. Okay. So this will be the Maxwellian distribution of velocities for electrons traveling in plus x direction from source to drain, and this will be the Maxwellian distribution of velocities for electrons traveling from drain to source. The only difference is in EFS and EFD. Okay. So this tells us about something important, and here generally in MOSFET we are concerned only about this point, which is the top of the barrier. So for this point EC becomes EC0, and these functions will give us the probability that a positive velocity electron is there. So this will be the probability that an electron with velocity Vx and Vy is traveling in positive x direction, and this will be the probability that an electron is traveling in negative x direction with velocity Vx and Vy. Now let me show you something important here. So this is the plot of the Maxwellian distribution of velocity for various drain voltages. So this is the plot for VDS equal to 0 volts. This is for a very small VDS 0.05 volts. This is slightly larger VDS 0.1 volts, and this is a very high VDS 0.6 volts. And this is the key to understand the velocity saturation in the ballistic MOSFET. So when there is no drain voltage, VDS is 0 volts, in that case this distribution function FVX Vy, in this function both positive components and negative components are equal, and as you can see in this 3D plot here that this is exactly a symmetric distribution of velocities, and so the number of electrons or the electrons having positive velocity, the probability of electrons to have positive velocity and the probability of electrons to have negative velocity is the same. So the net velocity is 0 in that sense, and that is the equilibrium condition. When a small VDS is applied, in that case this EFD goes down a little bit, and that essentially reduces this. This EFD minus EC0, this actually this screwed things are now screwed. Now F plus and F minus are not the same, and as you can see here that now more electrons have positive velocity as compared to the negative velocity. So there is a net current in the MOSFET. For slightly larger VDS, the negative velocity electrons drop down abruptly and only the positive velocity electrons are there, and finally for higher values this totally diminishes, the negative component totally goes away and only the positive component is there. And this is the situation when the negative component is totally gone away. This is the case when the velocity is saturated, because even on increasing VDS further, the velocity, the net velocity will not increase, because the net velocity is the difference between the positive and the negative functions here. So at a certain VDS, this negative component goes to 0, and that essentially saturates the velocity in the MOSFETs. So I'll let you think more about this, and in the next class we will conclude this discussion and we will start with the electrostatics part of the MOSFET, and that will put everything together so that this MOSFET theory becomes clear. So that's all for the day. Thank you for your attention. See you in the next class.